Today we're going to talk about arcs and chords and some relationships between those. So yesterday we defined what an arc is. A chord we defined back a few lessons in lesson 1. And today we're going to talk about some theorems that relate arcs and chords within a circle. So the first theorem says, in the same circle or in congruent circles, two circles that are the same size, says that congruent arcs have congruent chords and vice versa. So what that means is, within this circle, if I have two chords that are the same size, then the arcs across from them are the same size. So for example, if both of these chords have a length of 7, and let's say this arc has a measurement of 100 degrees, the other arc would also have to have a measurement of 100 degrees. Okay? So if the two chords match, the two arcs match. If the two arcs match, the two chords match. Okay? They do not all four match each other because we use different units of measurements. They're different kinds of things. But the two chords match and the two arcs match. Yeah.
In order to measure an arc, wouldn't you need an angle to have it like across from?
That's one way to find the measurement, is to say that it's the same as the central angle, but it could also just be provided. Our second theorem says that a diameter, what is a diameter again? What's a diameter?
A chord that goes through the middle of a
A chord that goes through the center. So a diameter is a chord, but it's a special chord because it goes through the center. So a diameter that is perpendicular to a chord bisects the chord and the arc. So if we have a diameter that hits a chord at a right angle, that chord is going to be cut into two equal pieces, and the arc will also be cut into two equal pieces. The theorem specifically says diameter, but we don't really need the whole diameter. We're not really using half of this picture, so we could actually erase this other part and then just say that it works for a radius also. And if a radius is perpendicular to a chord, then the chord will be cut in half and the arc will be cut in half. This is what a majority of your homework problems are going to look like, is this picture. Theorem 9.6, and we'll do some examples of the types of problems that you'll see. Theorem 9.6 says that in the same circle, or two circles that are the same size, chords that are equally distant from the center are congruent. So to find their distance from the center, what we need is our center, and then we're going to go out some distance away from there and make a perpendicular chord. Then I would go out that same distance in a different direction and make another perpendicular chord. So that from the center, those two lengths are the same. And this theorem says if those two lengths are the same, then the two chords are actually equal as well. Okay? And vice versa. If the two chords are equal, then they must be the same distance away from the middle. Several of these theorems have used the word perpendicular, so we're talking about right angles are going to be important to us. Right triangles are then going to be important to us in this lesson. We're going to be looking for right triangles within our picture to solve for. So we'll do some examples now. In our first example, we'll have a circle named O. When we name the circle, we're naming the center. I'm going to have a chord, AB. And I'm going to go perpendicular from O to that chord. I'm going to call that point where they meet M. We're given that AB is equal to 16. OM is equal to 6. And we want to find the length of a radius. Okay, first, if AB is equal to 16, what does that tell us? MB is 8, and also AM is 8. So one of our theorems said that when a diameter or a radius or even part of one hits a chord at a right angle, hits it perpendicularly, then it bisects that chord. So that 16 is going to get split equally over that AB. Okay, so we get 8 and 8 there. OM is 6, so we can label that in. And we're asked to find a radius. Where would a radius be?
The hypotenuse of the triangle.
The hypotenuse of the triangle. So we could draw one in at OA, or we could draw one in at OB, and it doesn't matter which one we draw in because they're going to be the same. All radii within a circle are the same, so we just want to pick one of those and draw them in the same. So we get a right triangle then, and if we're looking for the hypotenuse of that right triangle, how do we find it? Pythagorean theorem. And make sure that when we do the Pythagorean theorem, the hypotenuse is always the one that's alone. So we're going to do 6 squared plus 8 squared equals c squared, since we're looking for the hypotenuse in this picture. 36 plus 64, which is 100. So that radius length is going to be 10. Yes.
In this case, it does work. If you just subtract them, you get 10, but that usually doesn't work, right?
Correct. Yep. It's a convenience here, but it's a special case. Good thought, though. I like looking for shortcuts and patterns.
My answer was right. I said it looks about 10.
Oh, never trust your eyes on my pictures. Goodness. Don't even trust them on the book's pictures, but definitely don't trust them on my pictures.
I'm guessing game is super.
All right, and this one, we are given PQ is 10. Like the last problem, I guess I didn't draw in my little, with my little right angles in there. Like the last problem, since we have right angles here, we can split that chord up equally. So instead of 10, we can call that 5 and 5. Our radius is 13. Again, like the last problem, it's not drawn in, but we can draw in anywhere that connects the center to the edge, and that will be a radius, and they're all the same. They're 13. We're looking for OM, so we get a right triangle again. In this right triangle, which part is the hypotenuse?
13.
The 13. So we need to make sure that the 13 is alone, and we do the 5 squared and x squared together. 169 equals 25 plus x squared. Subtract that 25 gives 144, and the square root gives 12. Questions on either of those examples?
Is that all they're going to be?
Nope, we have a few more examples of different things that you could see.
Sure.
Alright, on this one we want to find two things. So we have our diagram provided, and within the diagram we're given a length of 17 and a length of 15. First thing we're asked for is RT. What will that be? 30. Because MT is 15, and I should have drawn in my little right angle here, and we're hitting at a right angle, our theorem says that each of those two pieces are going to be the same. The chord's going to be bisected, so if each piece is 15, then together that gives 30. And if I'm looking for OM, that's right here. and we end up with, once again, another right triangle. Right triangles and Pythagorean theorem are going to be very important to you throughout the assignment. What is the hypotenuse of that right triangle?
17.
17, so that's up along the lone. 17 squared is 289, and 15 squared is 225. Subtract from both sides and we get 64 is equal to x squared. So x would be equal to then 8. Now, I have another question for you, a little bit of a bonus challenge here.
Do it again.
How long is an x?
Wait.
Oh, I know how to figure it
Would it be 9?
It would be 9. How do we figure 9?
Because the radii is 17, and then you just do the radii minus x.
Why?
Because OS is another radii.
Okay, so every time we connect the center to the edge of the circle is a radius, no matter what direction we draw it in. So OS is a radius, and all radii should be the same length. So if OT is 17, then OS should also be 17. And if we just found that x is equal to 8, then we could find the rest of that must be equal to 9. We don't have any way of finding that little portion directly, so if you need to find that little portion that's kind of outside of the right triangle, you would need to first find that right triangle portion and then subtract from the full radius. Okay.
We have problems like that in our homework.
Possible. I'm saying possible not to be like cryptic, but I actually don't know. I don't remember if any of them asked that. What's the 7?
The right triangle.
Oh,
Have you ever had an entire class in 11 on a project?
Oh, yeah. There's always one kid running.
Alright. Most of our questions, well really all of our questions so far have dealt with the chords and the theorems that have talked about chords, but some of our theorems also talked about arcs. So in this problem we're thinking about arcs. If I want to find the arc ACB, remember yesterday we learned that when we have 3 letters, that tells us our starting place, a pass-through, and an ending point. So if I start at A and pass through C and go to B, how could I figure out how big that arc would be?
360 minus 220.
360 minus 220. So the other side of the circle, we're told, is 220, going to A and B around the other way. So the whole circle is 360. 360 minus the 220 would leave what's left over for the rest of the circle. So 140. The next question asks us to find angle AOC. So we're looking for how big is this angle? From yesterday, what term do we use to describe this angle?
Central angle?
A central angle. It has its vertex at the center, it's a central angle, and what do we know about the size of a central angle? It's the same as the
Arc.
arc across from it. So how big is the arc across from that angle?
70.
70. One of our theorems today told us that when we have this perpendicular relationship between a radius and a chord, it's going to bisect the chord, and we've been using that fact, but it will also bisect the arc. So that 140 is going to split equally. So the arc is 70, which means the central angle is also 70. One more.
Is there some setting that you're using that as a spoon? You are dumb.
You are rolling.
Oh, this is not Hey, good night.
This one looks hard.
I know.
It's hard. It's hard. I know that. Why do you have the best?
All right, we have 2 chords. that are equally distant from the center. So chord AB and chord CD are the same distance away from the center of the circle. What does that mean about them? They're the same size. And if the chords are the same, what does that mean about the arcs across from them? They are the same. So arc CD is E. That's combining two different theorems that we learned today. So the first one said that if two chords are the same distance away from the center, they will be the same. And then a different theorem said if two chords are the same, then their arcs will be the same. So this is combining together two different theorems that we applied. Big idea in the homework, we're dealing with lots of right angles. So look for a lot of right triangles to do your Pythagorean theorem in your assignment. Your assignment is from 9-4, 1 through 13.